Hi, everybody. This is Ms. McClellan. We're going to go over note 7.2.2, probability. This video. All right, here it is. Now, in this lesson, we have several learning goals. Just to briefly tell you what topics we'll go over. We will review Venn diagrams. We will build two-way tables to represent a sample space. And we will calculate conditional probability. And last but not least, we will check for independence by using probability of A is equal to question mark, probability of A given B. Now, this is quite a long list. It's more than usual. And for that reason, I say most often these notes will take to in-class lessons, but still it will be just one video. Okay, so we begin with Venn diagrams. Now, Venn diagrams are probably familiar for you. We can represent events with a Venn diagram. It's a display of potential probabilities. The box around the Venn diagram represents the total sample space where the probability of something in the sample space happening is at probability of S equals 1. The circles themselves, and let's draw those in. We have A and B for our events and our sample space. So this is a Venn diagram. Now the probability of A, that's the entire, it's represented by the entire circle of A. The probability of B, that's the entire circle of B. The probability of A and B, that's the overlap where they occur together. So now we're going to do some examples of certain types of shading. Now, I'll be using these symbols, U, and that is read as union, and an upside down U, which is read as intersection. In spoken word, when we're in conversation with somebody, or is usually what you would say to represent union, and is usually what you would say to represent intersection. Let's see what that means. First, we'll just do the probability of A. We'll shade that in. Here's the probability of A. A could happen, so I shade A in. Then let's look at probability of A union B. That means or. Now, some of you will very reasonably think that the probability of A union B is this, but that's not complete. The reason you think that is, well, I mean, I can't read your mind, but the reason people think this usually is because in spoken word English, A or B means A or B, but not both. Like, do you want pepperoni or sausage pizza? You want pepperoni or you want sausage? But I'm not asking if you want both. Well, in math, or means A or B or both. So the intersection is allowed in the union. Okay, we have probability of A intersection B. This is A and be read at, the previous one would have been read as union, and this one would be read as intersection. And that would be the space where they overlap. And then from our last notes where we talked about complements, we have to think about the probability of A complement. Now, A complement means everything except A. So here's my circle A, and I'm going to do everything except that circle. Okay, moving on. Now we look at some more complicated probabilities. Now, Venn diagrams are actually not in the standards for California for IM2, but using Venn diagrams can make a lot of things easier. In particular, we see this probability of A and not B, probability of A intersection B complement. And we see this next one, probability of A complement union B. It might not be obvious, but we'll see in just a moment that this probability is 1 minus that one. I'll show you what I mean. So this means A and not B. As a drawing, A looks like this, and not B, and not B looks like everything that is not B. What we end up with is where these two things overlap. So A and not B is just this part right here. Okay, now let's look at A complement union B. Well, that means not A or is B. And with drawings, we have the drawing of not A, which is everything except for A. Oops, I just did everything except for B. Let me cross that out. Okay, sorry about that. Not A or is B. Now, or is additive because in math, or means this shaded area or this shaded area or both. So up here, anything that was shaded in our little drawings is allowed. All of B is allowed. And anything outside of A is allowed. So what we have is the opposite of our drawing to the left. And just looking at notation, that's not obvious. So one way that Venn diagrams can be useful for us is to make complicated notation more simple. Let's do one more. Probability of A complement intersection B complement. So we want not A and not B. Not A looks like everything that is not A. We're doing intersection, that's and. Let's see, not B. I'm recording. So we need to think about where we have overlap here. And it looks like it's just the outside. Here we go. Okay. Next problem. In this example, we get to use what we've been practicing. We're going to use Venn diagrams to solve for probabilities. So this one says, a study was done to see if students who have walked into the wrong classroom are more or less likely to have also mistakenly brought a pet to school in their backpack. Out of 200 students interviews, it was found that 125, so we have a total number of 200, 125 students have walked into the wrong classroom. 92 have mistakenly brought a pet to school in their backpack, and 74 are in both categories. Let's make a Venn diagram and answer the probability question. Okay, here's our Venn diagram. We're going to have sets A and B. Anytime we have a variable, we should probably define it. So let's let A equal students who have walked into the wrong classroom. Let's let B equal students who have brought a pet to school, have in their backpacks. And I'm just going to list the information we have. Okay, I know S equals 200 because I have 200 students. A has 125 elements. B has 75 elements. Is that right? 92, sorry. 92 elements. And A intersection B, we have that information too, equals 74. Now, a common error is to correctly put 74 here, but then incorrectly write 125 here. Yes, A equals 125, but that 125 includes the 74 in the intersection. So it's easier if you start with the intersection and then solve for what's here. What goes here is 125 minus 74, and that equals 51. Now, B is also a common error. B equals, the total of B is 92, 74 of which we've already accounted for. The pieces that we need still are 92 minus 74, and that equals 18. And if you notice, 51 plus 74 plus 18 doesn't equal 200. That's because there exist students who have neither walked into the wrong classroom nor brought a pet to school in their backpacks. And from our sample, 57 students have done neither. And I get that by saying 200 minus 51 plus 74 plus 18, which is 57. Okay. Part A, probability that a student has walked into the wrong classroom and brought a pet. That's right here. You don't have to draw a little drawing, but for me, it helps. The probability of that is not just 74. Remember, probability is a number between 0 and 1. You need to include the denominator, which is how many students there are in total. This answer is 74 over 200, or if you prefer, as a decimal, 0.37. Part B, walked into the wrong classroom or brought a pet. So for that, we need to add these three pieces together because anything in A or B is allowed. Remember, or is not exclusive in math, so that intersection should be included. So we have 51 plus 74 plus 18 over 200, which is 153. Did I say 53? I meant 43 over 200, which is about 0.715. And for drawing, because for many of us drawings help, that's what that would look like. Part C, walked into the wrong classroom, but did not bring a pet. So that's A is allowed, but not B. For us, that would be this section right here. Walked into a classroom, but B is not allowed, so I can't have the intersection. That's 51 over 200. And if you like, that's 0.255. Part D, probability of not walked into the classroom, but did bring a pet. So that's not A, but B is allowed. That'll be this section. And that equals 18 over 200. And the probability is about 18 over 200. And if you prefer, you can write it as a decimal, 0.09. Just two more, everybody. Okay. The probability that someone has not walked into the wrong classroom and not brought a pet. Well, that's everything on the outside because they've done neither thing. So that'll be these numbers here, these elements. And that equals 57 over 200, or approximately 0.285. Part F, probability walked into the wrong classroom or brought a pet, but not both. Well, walked into the wrong classroom, A, or brought a pet, B, but not both, so not the intersection. Okay, that would be 51 plus 18 over 200, which is 69 over 200, or approximately 0.345. Okay, we continue. Okay, so for this one, we have another example. A pizza shop has two sizes of pizza, large and small. On a certain day, a pizza shop made 59 plain pizzas, 72 pizzas with toppings. Of the 59 plain pizzas, 19 were small, and of the 72 pizzas with toppings, 42 were large. Oof, this is a lot of numbers. A pizza is chosen at random. Find the following probability. We'll make a two-way table and a Venn diagram. Okay, so my home base is Venn diagrams, but they have their limitations. Okay, we've got A and B. Let's let A equal a large pizza. Let's let B represent a plain pizza. Well, you know, I don't know what the intersection is, and that makes doing a Venn diagram rather difficult. So I'm going to start my two-way table because I want to see if I can find an easier way. So I've got pizzas, they're either plain or they have toppings, and they're either large or they're small. Okay, now I think I can start to fill in my numbers. Let's see. 59 plain pizzas is how many they made. That's a total. So if I add the large planes and the small planes, I'll get 59. Okay, I've used this one. 72 pizzas with topping, that's a total. If I add the large pizzas with toppings and the small pizzas with toppings, I'll get 72. Okay, I've used that number. 19 of the plain pizzas were small. I put that there. 72, of the 72 pizzas with toppings, 42 were large. So 42 will go here. All right, I got to figure out the rest. Let's see. I know I can figure out this one. That's 59 plus 72. That's the total number of pizzas. 131. Okay, I can figure out how many small pizzas with toppings I made by doing 72 minus 42. That's 30. I can figure out how many large plain pizzas I had by doing 59 minus 19. That's 40. And I like putting totals in my tables. So I had 82 large pizzas that day and 49 small. Okay. So let's see. If I want to fill in my Venn diagram, I can now. 40 pizzas were both large and plain. That's the intersection. 42 pizzas were large with no toppings. B is plain. 19 pizzas were plain and not plain and small. Let's see, 42, 40, 19. And I guess 30 is all the peaches that were small and with toppings. But this is confusing for me. So for some problems, I think a two-way table is much easier to understand. Anyways, you pick. Okay, let's find these probabilities. The probability that you get a large pizza. That is equal to 82 over 131 because there are 82 large pizzas and out of a total of 131. Probability of small. Okay, if you are a small pizza, there's 49 of you. That's going to be 49 over 131. Notice that for all of these, the denominator is the same. It's always 131. So let's just set that up. Okay, how many pizzas had toppings? 72. How many pizzas were plain? 59. How many pizzas were large and plain? Large, plain, 40. How many pizzas were small with toppings? Okay. How many pizzas were small or plain? Ooh, or. Careful with ors, everybody. So, for this, we need the general addition rule because these are not mutually exclusive. So you can be both at once. So that will be the probability of small plus the probability of plain minus the probability of small and plain. So that will be 49 over 131 plus 59 over 131 minus the intersection, small and plain, 19 over 131. And the reason we have to do that subtraction is because when you add 49 and 59, you're actually adding that 19 twice, and so I have to subtract it once. Otherwise, you double count it. And you only want to count things once. Anyway, you do all of these, and if you throw it in your calculator, which is what I did, you get 0.679. Okay. Large or with toppings. So that is large or with toppings. So the probability that you have, you're going to need your general addition rule again. So probability of large plus probability of toppings minus probability of large with toppings. And the probability of large was 82 over 131. The probability of toppings was 72 over 131. And the probability of large and with toppings was 42 over 131. And if you put all that in your calculator, you should get 0.855. Last but not least, small or large. Okay. Can you be small and large at the same time? No. These are mutually exclusive. So you can use the addition rule for mutually exclusive events. We have 82 over 131 plus 49 over 131. And would you know it, that equals 131 over 131, which is 1. Now, if you were called that the pizza place only has these two sizes, then you could have skipped right to telling me it was 1, because that's the whole sample space. Every pizza is either large or small. There's no medium. So the probability that you're one or the other is 1. But you would have to write a little sentence to explain it. Okay, next page. Okay, we've got the multiplication rule. You roll 2 die. You roll a die 2 separate times. The question is, what is the probability that you get an even number followed by a 5? And there's two ways to accomplish this. So first way, you could list your sample space. So if I roll a die and the first one is even, that's 2, 4, or 6, and the second one has to be 5. So my sample space is 36 because I know that when I roll a die, I end up with a 6 by 6 box of things that could happen. So I could roll a 1 and a 1, a 1 and a 2. Anyway, it ends up being 6 by 6 because there's 6 options for the first roll and 6 options for the second, and 6 times 6 is 36. Okay, so S is 36. And there are 3 possible ways to get an even number and then a 5. So the total possible ways that could happen, 3 divided by 36 is my probability. Another way to do that is with something called the multiplication rule. And that is, we know the first roll probability. That's 3 over 6, because there are 3 ways to get an even number. For the second roll, well, there's only one way to get a 5. That's 1 over 5. And you can multiply these two probabilities together. Not 1 over 5, 1 over 6. And if you multiply these two together, you get 3 over 6 times 1 over 6, which is 3 over 36. If we want to find the probabilities that 2 or more events occur together, then we multiply their probabilities, which is to say that the probability of A and B is equal to the probability of A times the probability of B. However, that only works if the events don't influence each other. So far in our class, every example we've had, this equation would have worked for it. But we're going to get to a place where and we'll have 3 more examples where this works. But then we're going to talk about something called conditional probability, and it gets a little bit more complicated. Okay, for these examples though, it's going to work. I roll 2 die, 1 red and 1 green. What's the probability that I roll a red 1 and a green 5? Well, the probability of a red 1 is 1 over 6. And the probability of a green 5 is 1 over 6. So the probability that I roll a red 1 and a green 5 is 1 over 6 times 1 over 6, which is 1 over 36. A coin is flipped and a die is rolled. What is the probability that the result is a head and a 6? So the probability of heads is 1/2. The probability of a 6 is 1/6. This answer is 1/2 times 1/6, which is 1/12. Okay, what is the probability that a couple will have 4 boys in a row? Yikes. This is a weird problem. I don't like this problem. I'm gonna take it out. Cross it out. I'm not doing it. Okay, next problem. Dependent events, conditional probability. In previous examples, we assume the events do not influence one another, meaning the events are independent. But what if they do influence each other, everybody? Okay, so it happens to be that real world probabilities can be a lot trickier to navigate. The conditional probability of an event is the probability that one event will happen if it is known that another event has happened. The symbol for that is probability P of parenthesis A, vertical line B, and here the vertical line means given. So I would read that as probability of A given B. I would read that as the probability of A given B. Okay. Next page, we continue. Dun, 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 dun. Now, the formula for conditional probability is probability of A given B equals the probability of A and B divided by the probability of B. Or symmetrically, the probability of B given A equals the probability of A given and B divided by the probability of A. And you might be thinking to yourself, what? What? Well, here's why. When you know something has happened, it changes the sample space. In particular, the sample space shrinks to the given event. So the probability of P and B, the probability of A given B, well, if we know B has occurred, then the denominator becomes B. So the probability of A given B has a denominator of B and now I want the probability that A happens. Well, now the only way A could happen is in that intersection. So it's the probability of the intersection divided by what we say has already happened. Okay, let's look at the multiplication rule for dependent events. Once we have the conditional probability formula, we can rearrange into a new formula for finding intersection of two events. So we have the probability of B times the probability of A given B equals the probability of A and B divided by the probability of B. Sorry. Probability of A given B equals the probability of A and B divided by the probability of B. If I multiply both sides of this equation by the probability of B, then on the right-hand side, the probability of B cancels. And what I end up with is that the probability of A and B equals the probability of B times the probability of A given B. This is called the multiplication rule for dependent events. Let's look at some examples so that this can start to make sense for us. Okay, so let's look at hair color and eye color. If we select somebody and they have brown hair, what is the probability that they will also have hazel eyes? Okay, well, in this situation, the denominator is all possible people with brown hair. And the numerator would be 29, because that's all of the people with hazel eyes who also have brown hair. This would be the probability of hazel eyes given brown hair. And if you prefer a decimal, that's about 0.203. Okay, if you select a woman and she has brown eyes, what's the probability that she also has black hair? So this would be the probability of black hair given brown eyes. And that would equal, well, I know she has brown eyes. So the number of people with brown eyes is 122. And out of those people, 36 have black hair. So 36 over 122 is my probability, and that's approximately 0.295. Next problem, next page. We're zooming along. Okay, last page. Showing independence. So most of the time it will be hard to intuitively decide if two events are independent or not, but we have a way we can prove it. So independent. Excuse me. Sorry. Okay. So we know that based on our independence, if two events don't depend on one another, then the probability of A intersection B should equal the probability of A times the probability of B. And from conditional probability, we know that the probability of A given B is equal to the probability of A and B divided by the probability of B. What we're going to do is we're going to use substitution, and we are going to substitute probability of A times B into my conditional probability formula. So and that would give me that the probability of A given B is equal to the probability of A times the probability of B divided by the probability of B. But probability is just a number, so this can cancel. And what I end up with is if two events are independent, meaning if this value is equal to that value, then the probability of A given B is just the probability of A. So to show or justify independence, we want to prove or disprove that the probability of A given B equals the probability of A. If this relationship is true, then the two events are independent. If this relationship is false, then the events are not independent. So everything depends on the truth value of this equation, which kind of makes sense. If A and B are independent, you would assume that A given B is the same as A, because knowing B shouldn't impact anything about A. Okay, let's look at this last little example area. Examples. A study was conducted to investigate the relationship between a person's age and their preferred mode of transportation. Well, clearly, this is not the table that I meant to put here. So we're investigating the relationship between a person's thickness of crust preference and whether they prefer meat or vegetarian pizza. Okay. Are the events vegetarian and thick crust independent? Let's see. So we want to check, is the probability of vegetarian given thick crust equal to just the probability of being vegetarian. So for the left-hand side of my equation, I have the equation probability of vegetarian and thick crust divided by the probability of thick crust. And I want to check if that's equivalent to the probability of vegetarian. And that one's pretty fast. That's just 25.8 divided by 61.4. Okay. So here I've got vegetarian and thick crust. That's 11.6 divided by thick crust, which is 21.4, which is equal to, let's use our calculators, 11.6 divided by 21.4. That's equal to 0.54. And 25.8 divided by 61.4. And this is equal to 0.42. Now, these are not the same number. 0.54 does not equal 0.42. Therefore, the events are not independent. Okay, last problem, and then we're done. Okay, the probability of A is 0.44. Probability of B is 0.22. And A and B are independent. What is probability of A or B? Woof. All right, we can do this. So the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. These are independent, so I know that the probability of A and B is just the probability of A times the probability of B. Therefore, I can make this problem into P, A, or B equals to probability of A plus the probability of B minus, sorry, that should have been a P, the probability of A times the probability of B. So that's 0.44 plus 0.22 minus 0.44 times 0.22. And if I throw that in my calculator, I get 0.563. And then we're free. So we've gone over a couple of things. We did conditional probability. We made some two-way tables. We proved independence. All in all, it's been a pretty dense lesson. So try hard on your homework problems, and we'll go over what questions you have next class. Okay, thanks so much for your time, everybody. See you next time. Bye.